Okay, so now we know how to deal with this second order ODE with this term, non-zero term, right, on the right hand side. So again, a physics example, right? So just now, we have this oscillator with damping, right? So is this whole equation here, this whole left hand side equals to 0, right? So that's the case that we just saw. So now, this is again another physics problem that you have seen, I believe, is that now I have the oscillator, but with an external driving force. Okay, external driving force. So, and the external driving force goes like sinusoidally, right? So the external driving force also given by this cosine, cosine. So now we will have to solve this equation. Okay, actually, we have to divide by m. So mathematically, right? So mathematically, how do we solve this ODE? Right. So we have learned that first of all, treat the right hand side to be 0. Right. Find the complementary solution. Right. So and the complementary solution is something that we have found already in the last example. Right. So it depends on 3 cases. Right. So the whether it's under damped, critically damped, or over damped. But anyway, so these are the complementary solutions. Right. So it's always a linear combination of the 2 terms. So now, particular solution. Okay, so previously I told you that if this g of x is some cosine function, then the particular solution that you're going to try is some constant times that cosine plus some constant times that sine function. Okay. So then what you're going to do, okay, is that you plug in this, okay, back to the left hand side of the equation, right, and then compare with the right hand side, right. So to figure out what kind of A and B you need to pick in order to equate the 2 sides. So that's the idea. I'm not going to do the details here, right, but you'll be able to show that the particular solution take this form. So you may have asked, okay, why this is cosine sine, and then now I don't just have a cosine. Okay. But this is just using a trigonometric formula that you have learned, right? So because you have learned that cosine A minus B is equals to cosine B minus sine A sine B. So that formula. Okay. But anyway, so this is the particular solution. So what we can see here is that for the complementary solution, right? So the cosine term or the sine term are having a different frequency than this omega, right? So this omega, remember, is the omega, the frequency of the driving, right? The frequency of the driving. But this oscillator itself, the oscillator itself has the so-called natural frequency that I believe you have learned, right, which is given here. So then when you add the 2 together, right, so basically you have some oscillating term, right, at one frequency, and then add another oscillating term with another frequency. So, but actually, what you can see is that no matter which case you are at, okay, which kind of damping you are at, so this complementary solution in this case always come with this exponential decay factor, right? So that means no matter what kind of initial condition you give, right? So at the end, as t tends to infinity, so all this either of this, right, solution will die out, right? So, but here you can see that the particular solution itself does not come with this exponential decay factor. So that means it will keep going, right? So, and that physically, that's actually not difficult to visualize because you keep giving this driving force, right, over and over again. And because of this behavior, right, decay behavior, so then this one is also known as the transient solution. And this one is known as the steady state solution. So that means this one only survive, okay, for some finite time. And this one will survive forever. Okay. So this is known as the transient and steady state. So although, okay, so we are not going to do the details for this case, but I want you to notice one thing. So you can see that I have this square root term in the denominator, okay, and you can see that this denominator, if this denominator getting smaller, then this amplitude of this particular solution getting bigger, right? So that means that this amplitude, so that means this amplitude here. So how do you get the smallest denominator? Is that when your omega naught is equals to omega. So, and that is when your driving frequency is the same as the natural frequency of your oscillator. Then you get this term goes to 0, so then you have a very small denominator. Then you can have a very large amplitude oscillation. So that's the so-called the resonance, right? So I believe this is also you have heard of. So now one more special case that I want you to do by yourself is that I also have this gamma term. Right? This gamma characterize the damping of this oscillator. Right? So damping due to the air resistance that gives it this slowest down. Right? So now think of one situation is that if there's no damping, so no air resistance, then this gamma is 0. So this whole term is 0. And then also your driving frequency match the natural frequency. So this term also 0. So in that case, then this denominator is 0. So then this term blows up. So that means this whole thing, right, so goes to infinity. So then can we treat this as a solution here? So now I want you to go to work on this problem. Okay. So is that if we don't have damping, so I want you to re-examine the problem. Okay. So is that if I don't have the damping, so that means the no gamma. So gamma is 0, that means alpha is 0. So then the equation is become more simple, looks like this. And I want you to start from here. Just start from here. Okay, it's a simpler problem. Okay, but actually try to solve it for yourself. Okay, so I will give you some time. Okay, to try to find what do you need to find the complementary solution first, and then the particular solution. Okay, try this. Because we found that if you just start from here, right? So and then you will, although you solve the solution, but then you see that this one goes to infinity. So then let's take one step backward. Okay, so just look at this equation without damping at the first place. Okay, try to solve for the solution. Okay, so again, I should have put an m divided by m here, but that's okay. Let's say m is just 1 or something. Now, if I look at this, right? So first step, okay, no matter what, the first step is to look for the complementary solution. Right, the complementary solution. Then we just need to write down the auxiliary equation. Right, so this one. So that means the two roots are this. So then, first of all, if I don't care about the right hand side, right? So then this complementary solution is just some constant. Right, so A cosine omega naught t plus B sine omega naught t. So this is a complementary solution. So now, particular solution, right? So we try the particular solution to be what? Because I see the cosine term, right? So basically, so that means what I need to try some constant cosine omega t plus another constant times sine omega t. So what we need to try. But here, okay, so then you can, at this step, you might see a little bit of details that you need to be careful is that what if omega naught equals to omega, right? So that is actually the case that I was talking about. Right? So in the previous case, right, so I have this infinity problem, right? So that is, if you are going to do this, right? So you just assume that this is omega t and this is omega naught t. Then if omega naught is equals to omega, you run into trouble, right? Because that means the particular solution is linearly dependent with your complementary solution. But okay, so let me talk about that case in the next step. So first step, okay, so let me assume that omega is not equals to omega naught. Okay, let me first assume this. Okay. So with this assumption, then you will realize that this is easy. Okay, so because you just need to substitute this whole thing to the equation. So let me take the derivative. So dxp dt is alpha omega sine omega t plus d omega cosine omega t. Okay. So then the one more derivative, right? So d square xp dt square, so will be equals to minus alpha omega square cosine omega t plus beta omega square sine omega t. So that means, right, so d square xp dt square plus omega naught square x p would be equals to, right, so this whole term plus the omega naught square is xp, right? So and this whole thing has to be equals to the right hand side. Right? So what is the right hand side? Right hand side is f naught divided by m cosine omega t. So then let me just consider the term with omega t. So what do we have here? So the coefficient in front of this omega t term. So then I have this omega square and not square minus omega square, and then times alpha cosine omega t. And then of course you have some term with the sine omega t, but this whole thing has to be equal to this f naught divided by m cosine omega t. So then this one has to be 0 anyway. So then my alpha, right, so then my alpha times this omega naught square minus omega square has to be equal to f naught divided by m. So that means alpha is f naught divided by m. Right? So that's how you get the alpha, and the beta is 0. Okay. So then this is okay when we have this omega not equals to omega naught. Again, you can see that alpha, the denominator in the alpha also have this omega naught square minus omega square term here. So that means you run into problem again if you have this omega naught equals omega. That is, if you have omega equals to omega naught, then you need to try a slightly different form of the XP. Okay. So for omega equals omega naught, then the XP of t that you are going to try, okay, in order to avoid XP being linearly dependent with XC, then you have to multiply a t. You have to do this. So that's the problem. Okay, that's the problem. So if you, okay, I'm not going to do all the algebra again, but if you let this xpt to be this form, at the end you will find that your xp of t will be equal to, of course, you find that the alpha terms will be 0. Okay, and then what you have left is the beta term. Okay, and this beta is expressed in terms of f naught and this omega. So this is the form of your particular solution. Okay, when your driving frequency is exactly at the same as the natural frequency. So physically, what is it happening? So the particular solution also is a sine function, but its amplitude is increasing with time. Okay, you can see that the t is 1. So that means the oscillation amplitude of your oscillator, okay, so keep increasing. Okay, it increases indefinitely, and for sure, okay, at the end, indeed, okay, you will have an infinitely large amplitude. So that's actually true. So, and it does not happen. It does not happen if you have damping. So whenever you have damping, right? So, and that means your gamma is non-zero, right? So then your denominator cannot be 0, no matter what, right? Even you are at the natural frequency. So with damping, even your driving frequency is the same as the natural frequency. Okay, so the amplitude of this oscillator is constant, because although you keep giving it energy, but it just keep losing energy due to the air resistance. But here, right, so when you don't have the air resistance, right, and then you drive it at that resonance frequency, then this oscillator, right, so it keep gaining energy, but no place to lose energy, right? So it just keep moving at a larger and larger amplitude. But this only happen, okay, this only happen, okay, when this omega is equal to omega naught. Okay, and there's one more problem that I want you to try. If we don't have much time to talk about tutorial today, but the first problem, okay, I want you to try to look at first problem, the tutorial. So this problem is a bit different from what we had in the lecture notes, right? Because this time I don't just have a constant coefficient here. Okay, this P and Q are actually something that will find. Okay. But the question, first of all, only tells you that I don't tell you what P and Q, but I tell you the two solutions to this equation. Okay. And the first thing here, want you to prove that these two solutions are linearly independent. Okay, again, if you just take the ratio, you immediately see that. But here, the question really actually hope that you use the Wronskian. Okay, so the part one. Okay, try to use the Wronskian determinant. Okay, to show that these two solutions are linearly independent.